Today we are again solving systems of equations. We are still going to look at what is the ordered pair where these two lines would meet, but this time we're going to use the elimination method. In the elimination method, we are going to add the two equations together, and in the process of adding them together, we want one of the variables to eliminate. So when we add, like this one is perfectly set up for elimination. So if I add these straight down, x plus 2x is 3x, y plus negative y is 0, and 2 plus 7 is 9. The y completely eliminates, giving us an equation that we are able to solve. 3x equals 9, divide both sides by 3, we get x equals 3. Sometimes the system is set up perfectly for elimination, like this one was. We've got a positive y and a negative y. Those two will add together to give us 0. Sometimes the system is not set up perfectly for elimination, and we're going to have to do a little bit of work to get it ready. We're going to have to multiply the entire equation by something to get it ready. But this one was perfect. Now we just need to figure out why. And you have some options. You can plug 3 into the top equation. You can plug 3 into x in the bottom equation. It's entirely up to you. I think this top equation looks easier. So I'm going to use x plus y equals 2. Going to plug that 3 in. So 3 plus y equals 2. That means y equals -1. So the solution to this system is the point 3, -1. When you're solving by elimination, it is important to have your equations look the same. So it's best if it's something x, something y equals number. So in this second example, do you see how the bottom equation just isn't really in the right order? So our first goal is get this equation into the right order. I'm going to add x on both sides. I'm also going to add 8 on both sides. So I'll end up with x plus 4y equals 8. And I'm just going to bring this other one over so that I still have the two equations right on top of each other. If I add these two equations together right now, will one of the variables disappear? No, we'd have 2x, 7y, we wouldn't be in any better shape. We want to have a positive-negative match before we add them together. So I think it'd be pretty easy to get the x's to match, to be a positive x and a negative x. And honestly, changing from positive to negative is the easiest, because we can multiply everything by -1, and we can do that super easy by just going negative, negative, negative. Just take the opposite of every term in that second equation. Then let's add them together. X and negative x is 0. 3y and -4y is -1y. 5 and -8 is -3. So what does y equal? 3. Our y value is 3. We need to find our x value. We can plug 3 into the y of the top equation, of the original bottom equation, of the rearranged new bottom equation. I think I'm going to plug it into the top. That looks easier. I'm going to choose x plus 3y equals 5. Plug that 3 that we found in. And I get x equals -4. On this third example, if we added these equations together right now, nothing would disappear. And our goal is, when you add the two equations together, we want one of those variables to disappear. I like that I see a positive 3x and a negative 2x. It's nice when there's already a positive negative. We would just have to multiply both of them by something to get them to match. If we wanted to eliminate the x's, what would we need to make these two x's become? When you think of 3 and 2, the number 6 hopefully pops into your head. So if we were doing that, I'm not saying that we're going to, but that's one option. You'd multiply the entire top equation by 2. You'd multiply the entire bottom equation by 3, because your goal would be to get positive 6x on the top and negative 6x on the bottom. So that's one way that we could solve this system. Is there another way we could solve this system that maybe would involve less work? I see this y, I call this a naked y because it doesn't have a number other than 1 in front of it. Could I make that top y be a negative 3y? How would I make that top one be a negative 3y? Multiply by negative 3. So do you want to multiply one of them by negative 3, or do you want to multiply both of them? Just one of them? Okay. So if we multiply the top by negative 3, you have to multiply everything in the equation by negative 3. So negative 3 times 3x is negative 9x. Negative 3 times y is negative 3y. Negative 3 times 6 is negative 18. The most common mistake is that people forget to multiply that negative 3 to that number after the equal sign. And then I'm going to recopy this one just because I like to have them right on top of each other so that it's easier to do the math. Okay, let's add them together. Negative 9x and negative 2x makes negative 11x. Negative 3y and positive 3y, those are going to cancel each other out. Negative 18 plus 2 is negative 16. This one's kind of gross, isn't it? We finished solving by dividing by negative 11. Definitely going to need a calculator for this one. I get 1.45, and for it's 1.454545, so it's 1.45 repeated. You can just write 1.45. You can write 1.455. I would just round it to a place or two after the decimal. So my solution, the x value of our solution is the decimal 1.45. We need to find the y value. Which equation should we plug this into to get the y value? Which top one? The original top or the new top? I would go to the original top equation. This original top equation has a plain ordinary y, so I am going to use 3x plus y equals 6. So 3 times this x value, 1.45, plus y equals 6. 4.35 plus y equals 6. I get y is 1.65. This system, honestly, is why the elimination and substitution method exist. If we had to graph this, how difficult would it be to find that point precisely as the solution? Those points would not be, that point would not be easy to find on a graph. When I look at this last system, we're going to have to do a little bit of work to get this ready for elimination. It's not set up well for substitution either because there isn't a variable that has a 1 in front of it. Do we want to try to make the x's go away, or do we want to try to make the y's go away? If we want to make the x's go away, 2 and 3, we're probably going to be shooting for 6. If we want the y's to go away, 4 and 5, we'd be shooting for 20. 6 is smaller than 20, so let's shoot for 6. So my goal is to make these two become 6x and negative 6x. So I'm going to write this right here and say this is my goal. My goal is to have 6x and negative 6x because those would eliminate. How do I make 2x become 6x? We'd have to multiply by 3. How do I make the bottom 3x become negative 6x? Multiply by negative 2. Okay. So 3 times 2x is 6x. That's what we wanted. 3 times 4y is 12y. 3 times 3 is 9.
So if you like switch the negative 6 on top,
that's totally fine. So the question is, what if you decided to multiply the top by negative 3 and the bottom by positive 2? Totally fine. Your work might look a little bit different than other people's, but you're still going to eliminate the x, and that's still going to be fine. Negative 2 times 3x is negative 6x. Negative 2 times 5y is negative 10y. And negative 2 times 1 is negative 2. So we achieved our goal of getting our x's ready to eliminate. 6x and negative 6x, they cancel each other out. 12y and negative 10y is 2y. Oh, yay, another decimal. This one's at least a nicer decimal, isn't it? 3.5. So our solution is going to be something, comma, 3.5. Once you find one of them, you've got some choices. You could plug 3.5 into the original top, the original bottom, the new top, or the new bottom. I would recommend that you do not plug it into one of the new ones because we made those numbers bigger, and bigger numbers are harder to do math in your head. I want to go for the equation that has small, preferably all positive numbers. So I'm going to choose 2x plus 4y equals 3. You could choose the bottom equation. That's totally fine. 2x plus 4 times my y value of 3.5 equals 3. 2x plus 14 equals 3. 2x equals negative 11. I really picked some great numbers, didn't I? So x equals negative 5.5. Now remember yesterday, we had a situation where the variables all went away and we had either a true statement or a false statement. That can still happen with elimination. What if we had done all of this and instead of negative 10y right here, it had ended up being a negative 12y? Then both variables would have eliminated and we would have had 0 equals 7. That would have been a false statement, so that would be no solutions. So just like yesterday, if all of your variables go away and you have a true statement, it is many solutions. So you may want to write somewhere on here, if all of your variables go away and you have a true statement, that means many solutions. If all of your variables go away and you have a false statement, that means no solutions. So that can still happen with the elimination method.